Hello everyone, my name is Ankit Nimji. I am going to present this paper titled Deep Learning for Healthcare: Review Opportunities and Challenges for the course Topics in Data Sciences at UMass Lowell. This will be my agenda for this presentation. I will start with a brief introduction to deep learning in healthcare along with its uses. Later, I will talk about its applications, challenges, future scope, and finally end with a conclusion. Let's start with an introduction to deep learning in healthcare. According to many notable scientists and researchers like Andrew Ng, Hinton, Ade Adamson, deep learning is going to take over many human jobs like radiologist, pathologist in the medical field and give better results and thus help human mankind by providing better healthcare. So let's see what is this all about. So let's talk about the complex and skilled practice of medicine, its process and how many phases we need to go through to diagnose a disease and its treatment. Let's say you have some medical problem and you go to a general physician and you will be asked some questions like what's the problem? What's your patient's history? Have you had this before? What symptoms you have? You have cough and much more. Then doctor might say there's something wrong and starts a general method of first treatment with basic instruments like maybe he'll use stethoscope and a BP monitor, and then he might say that he needs some more tests done and he has doubts about the possible problem and asks to get those reports done by a pathologist. For example, he'll say, get me an x-ray. You then go to an x-ray center and get x-ray done. Then you meet with a radiologist who prepares a report about more possible problems. For example, he discovers some problem in the chest, maybe some symptoms of fluid effusion, and prepares a report. Then you go back to the doctor with a prepared report and the doctor says it looks like maybe TB but not sure and asks to get some tests done at the pathology for more surety. You then go to pathology and get blood samples done. You get biopsy done. You get some pathology tests done. Later is goes to the lab and blood might go to blood counting machine or microscopic image of some tissues and finally prepares another detailed report. Then you go to the doctor again, and if he's smart enough and discovers what you have in is a cancer, then he might say let's take a genomic test because what you have is some hereditary problem or disease to figure out some plan for a targeted treatment that might work on it. After all this, he could give you some medications to cure your problem or put you in the ICU for monitoring to get more data as problem could be a pretty serious issue and he might suggest you a surgery. The reason behind explaining this is in one way or another we are dealing with data in every phase of detecting and diagnosing some particular problem. In radiology tests, there is a data in the form of X-rays, MRIs, or other tests. In pathology tests, there is data in the form of blood tests, tissue samples, the reports, etc. Thus, take any phase, there is data that directly or indirectly interfered with humans to deal with it. There are problems in almost all phases, like not having enough physicians available, clinical data might be erroneous, the diagnosis made is very subjective, you don't really know which treatment is really going to work on you when the problem is very fatal and life-threatening. So, why should we use deep learning in healthcare? With successful experimental results and wide applications, deep learning has the potential to change the future of healthcare. The use of artificial intelligence has become increasingly popular and is now widely used. For example, in cancer diagnosis and treatment, deep learning for computer vision enables more precise medical imaging and diagnosis. Researchers at the Mount Sinai School of Medicine have developed a deep neural network capable of diagnosing crucial neurological conditions such as stroke and brain hemorrhage 150 times faster than human radiologists. A team of researchers at Analytic introduced a device that surpassed the combined abilities of a group of expert radiologists at detecting lung cancer nodules in CT scan images. They achieved 50% higher detection rate in testing conditions. In another case, researchers created a medical concept that uses deep learning to analyze data stored in EHR and predict heart failures up to 9 months before doctor scan. Based on analyzed work, it can be stated that deep learning approaches could be a medium for translating big biomedical data into improved human health, although there are some limitations and need more development. Before talking further about deep learning, let's see what makes deep learning different than artificial neural network. We can say deep learning and artificial neural networks are similar in operations, but deep learning is more capable in terms of results and details. Artificial neural network is a machine learning algorithm inspired by the working of the human brain, which enables a system to learn from some observational data. A simple neural network consists of an input layer, a single hidden layer, and an output layer. It is generally optimized for specific tasks and is usually not generalizable. On the other hand, deep learning is a machine learning technique that performs learning in more than two hidden layers. It is a deep neural network consisting of multiple layers of non-linear processing units, which is also called as hidden layers. It performs feature extraction and transformation. Each successive layer of deep learning neural network uses the output from the previous layer as input. The key aspect of deep learning is that these layers of features are not designed by human engineers, but they are learned from data using a general purpose learning procedures. Deep learning is a part of the machine learning family. It is based on data, learning representations, and methodologies. In deep learning, there are three major classifications, which are supervised deep learning, unsupervised deep learning, and semi-supervised deep learning. Deep learning is mainly used in recognizing speech, natural language processing, computer vision, social media networks, medical analysis, the design of the drug, bioinformatics, machine translations, game programs on board, and inspection of materials. Now let's see applications of deep learning in healthcare. There are four major primary fields in the applications of deep learning in healthcare, which are clinical imaging, electronic health records, genomics, and mobile wearables. Let's see their sub-applications one by one. Let's talk about clinical imaging. Clinical imaging is the practice of creating visual representations of the interior of a body for medical analysis and intervention, or to assess how organs or tissues function. Practitioners use medical imaging to reveal internal structures so they can diagnose and treat diseases. Medical imaging also contributes to a database representing normal anatomy and physiology, facilitating the identification of abnormalities. Medical imaging generally refers to non-invasive techniques for producing such images. Radiology techniques used for medical imaging include radiography, also called as X-ray, magnetic resonance imaging, also called as MRI, ultrography, also called as ultrasound, and endoscopy. Medical imaging generates large volumes of data, accounting for over 90% of all medical data. A number of medical images that emergency room radiologists have to analyze can be overwhelming, with each medical study involving up to 3,000 images taking up 250 GB of data. Radiologists can make use of deep learning to help sift through the data and analyze medical exams more efficiently. Deep learning networks can extract and process data at a speed and scale that is not humanly possible. One of the main uses of clinical imaging is cancer detection. Some of the deadliest forms of cancer, such as melanoma and breast cancer, are highly curable if diagnosed at an early stage. Thus, cancer treatment can benefit from the speed and accuracy of deep learning assisted diagnostics. Deep learning algorithms can be used to detect the characteristics of metastatic cancer with higher accuracy than human radiologists. One common use of deep learning for clinical imaging is breast cancer detection. Breast cancer screening typically involves comparing two mammogram images to identify points of abnormal breast tissue. This process can be facilitated by a trained convolutional neural network. Another example is Lymph Node Assistant, which is also called as LINA, which was developed by researchers at MIT. LINA was trained with data sets of pathological slides. Once trained, it was able to halve the time spent reviewing each slide and could recognize characters of tumors in just 1 minute. Lina has a 99% rate of accuracy for identifying metastatic cancer and locate even small metastases that a human pathologist might miss. In MRI image processing, high quality interpretation is needed to extract value from medical imaging, but the human interpretation is limited and prone to errors. While medical imaging such as MRI is typically used alongside computer analysis, standard MRI analysis requires hours of computing time. To align two MRI scans, a computer has to sort millions of voxels, which are 3D pixels, and it is time consuming to scale this up and analyze data from a large number of patients. However, you can train neural networks to pick up indications of same diseases. The data is fed into one end of the network and then passes through multiple nodes to produce the desired output. This allows radiologists to accelerate MRI image processing. For example, the voxel morph system. Voxel morph system, developed by researchers at MIT, is trained with 7,000 MRI brain scans, allowing it to identify common anatomical patterns. Represented by a group of voxels, voxel morph can process an MRI analysis in 2 minutes using a regular CPU, or in less than a second if run on a GPU. Deep neural network can be trained to identify tissue abnormalities based on relatively small number of clinical trials. This helps reduce the need for invasive measures to monitor and treat diseases. For example, a deep algorithm can help predict tumor proliferation using tumor probability heat map, which classifies the tumor probability of overlapping tissue patches. The images produced reveal the feature of the tumor, including location, shape, area, and density, to track changes. Informative data on different tumor features such as shape, area, density, and location, thus facilitating the tracking of tumor changes. Deep learning can also potentially enable the automation of progress monitoring. Electronic health record systems, also called as EHR systems, store patient data such as demographic information, medical history records, and lab results. EHR systems improve the rate of correct diagnosis and the time it takes to reach a prognosis via the use of deep learning algorithms. These algorithms use data stored in EHR systems to detect patterns in health trends and risk factors and draw conclusions based on the patterns they identify. Researchers can use data in EHR systems to create deep learning models that will predict the likelihood of certain health-related outcomes, such as probability that a patient will contract a disease. There are two ways to use EHR systems data. First, a static prediction. A static predictions tell us the likelihood of an event based on a dataset researchers feed into the system and code embeddings from ICD, which is the International Statistical Classification of Diseases. For example, a scientist named Coy fed a deep learning model with the present representation of a patient created from EHR data, specifically their medical history and their rate of hospital visits. Based on this information, the system predicted the probability that the patient will experience heart failure. Another way is a prediction based on a set of inputs. Data from the EHR system is used to make prediction based on a set of inputs. It is possible to either make a prediction with each input or with the entire dataset. For example, Coy developed Doctor AI, a model that uses artificial neural networks to predict when a future hospital visit will take place and the reason prompting the visit. They base this prediction on the information including ICD codes gathered from a patient's previous hospital visits and the time elapsed since the patient's most recent visit. Let's talk about genomics. The human genome comprises more than 3 billion base pairs. Recent technological advances have increased the understanding of genome biology to an incredible degree, exploring the connection of genotype to phenotype. Predicting regulatory function and classifying mutation types can lead to better understanding. Deep learning has been successfully implemented in areas such as image recognition and robotics, for example, self-driving cars, and is most useful when large amounts of data is available. In the same manner, using deep learning as a tool in the field of genomics is entirely suitable. Thus, we can say deep learning in genomics has the potential to enlighten fields such as cancer diagnosis and treatment. The availability of a vast source of data of various types such as DNA, RNA, methylation, chromatin accessibility, histone modifications, chromosome interactions, and so on. They are also known as functional genomics. It ensures that there is enough training data set to build accurate prediction models relating to gene expression or genomic regulation. Other features such as identification of long non-coding RNAs or splice site prediction can also be analyzed. As more data become available, better models will be able to be trained, thus resulting in even more precise and accurate predictions of genomic features and functions. Deep learning made a great contribution in understanding gene regulation, genome organization, and mutation effects, not only in functional genomics, but genomic information is also used in plant or population genomics. Let's discuss mobile wearables. Wearables in healthcare typically collect the data, monitor it, and interact with users. It provides timely awareness on various health parameters to the user and physician. For example, real-time health monitoring wearable sensors, fitness wearables, wearables for elderly care, etc. Wearables in healthcare industry are using AI to improve the quality of life in various ways. Let's take an example of AI-powered diabetes eye disease detection from researchers in the Google Brain Initiative. In this system, mathematical algorithms, which are based on deep learning, uses neural networks to learn and perform a particular task by repetition and self-correction. This mathematical algorithm is trained with over 100 human-grade images, which shows various levels of retinal hemorrhages caused due to high blood sugar levels. A severity grade is aggregated by the algorithm to each image, and then comparison is done with a previously defined grade from the training set. Parameters are then modified slightly to decrease the error on that image. This process is repeated for each image in the training set many times over, allowing the algorithm to learn how precisely compute the diabetic retinopathy severity from the pixel intensities of the image for all images in the training set. Another example is next generation variables for blind people. These variables detect obstacles on the user's path using ultrasounds and notify them about those obstacles so users can safely navigate around objects around them. Another example is AI-enabled smart Bluetooth headphones that develop as fitness tracker are featured with biosensors that detect heart rate, elevation, motion, proximity, and touch. These, these headphones have AI-based personal trainer, which helps in working out in a smarter way by providing real-time tracking of running, cycling, and other exercises. Depending on the health parameters, these headphones suggest the ideal path to achieve your individual fitness goal. As it looks like there are many interesting benefits of deep learning in healthcare, but there are many challenges associated, like data volume, data quality, data variability and its limitations, and also temporality. Let's discuss each one. Data volume is one of the challenges which directly depend on data set quantitatively. If we talk about imaging in radiology, there are much bigger files than regular images. Digital pathology data can be of a size of 5 GB if we are talking about 10K across 10K. A high resolution CT scan image with 100 to 200 slices or could be more goes anywhere more than 1 GB. Mammogram images are typically 12-bit images. Then we have MRI sequences. MRI sequences are a different way of obtaining MRI images. You can change parameters and visualize them in different ways. Each MRI image is a 3D image. So if I am talking about multiple MRI sequences, we have 40 images. Because of all these points, we have to deal with problems like a large number of voxels. We have to extract large numbers of features. Then there is a course of dimensionality and huge computational load. Also to add, we have more than 7.7 billion people all over the world, with a great part not having access to primary health care. Let's talk about data quality. Opposite to other domains where the data is clean and well structured, healthcare data is highly heterogeneous, ambiguous, noisy, and incomplete. Training a good deep learning model with such massive and variegated dataset is challenging and needs to consider several issues such as data sparsity, redundancy, and missing values. Third point is limited data with large variability. There is very limited data and with huge variability. For example, people wearing religious necklaces or someone with birth defects will change their MRI or CT scans in a way that deep learning models will classify them in some other group, and later it could be very easily misclassified in something else. Then we have demographical variation and also cost of privacy. And then we have temporality. As we know, the diseases are always progressing and changing over time in a non-deterministic way. Developing deep learning solutions which can handle temporal healthcare data is an important aspect that will require the development of different solutions. Let's move to future scopes of this paper. Uh, as intriguing as these pilots and projects can be, they represent only the very beginning of deep learning's role in healthcare analytics. Recently, researchers of Google and two medical schools did a study with data from electronic health records, applied deep learning algorithms, and obtained much better accuracies with predictions in those areas than human doctors. This research has been a great source of inspiration in the medical community. The Office of the National Coordinator, also called as ONC, is one organization with particular high hopes for deep learning, and it is already applauding some developers for achieving remarkable results. On the clinical side, imaging analytics is likely to be the focal point for the near future due to the fact that deep learning already has a head start on many high-level applications. Voice recognition and other analytics based on deep learning also have the long-term potential to provide some relief to physicians and nurses struggling with their EHRs. Deep learning has a tremendous future ahead in the field of medicine. We are barely scratching the surface, making some slight improvements in various areas within healthcare. With the standardization of data, better access to all data like EHRs, claims, and medication details, researchers and doctors will be able to make a better prediction about human diseases, and patients can take preventive measures such much ahead. It won't be surprising to see in the near future that average human life expectancy has increased by 20 years, which been made possible by advanced AI techniques and deep learning. With an extremely high number of promising use cases, strong investment from major players in the industry, and the growing amount of data to support cutting-edge analytics, deep learning will no doubt play a central role in the quest to deliver the highest possible quality care to consumers for decades to come. After a detailed study on this paper and references, I can conclude that deep learning could be an element for translating biomedical data into improved human healthcare. On the other hand, the latest advancements in deep learning technologies provide new useful and effective paradigms to prove the end-to-end learning models for uncertain and complex data structures. I thus end my presentation here, and thank you for your time.